Chasing out of space. Get your head around it. Compound elements, what's their place? Get your head around it. Chemical explosion, gravity in motion. Get your head around it. Get your head around it.
Today on Scope, we are going up and into space. We find out everything you wanted to know about black holes, make a constellation, find out about gravitational waves, and see how you go about reusing a rocket. Hello there and welcome to Scope, a show all about the possibilities and the probabilities of our world, as written and illustrated by science. Oh, and you'll have to excuse me, I'm actually on my way out. I mean, the whole episode is quite literally out of this world, being on space and all. But first, of course, you've got to get there. And to that end, I'm about to catch up with an Aussie astronaut, Andy Thomas. And I'm just a little bit excited about it. Dr. Andy Thomas.
How do you do?
It is a pleasure to meet you, Australian astronaut. Now, look, I've got so many questions, so I'll try and narrow it down to the most important ones. Tell me, when you were growing up, did you, like so many kids, have that dream of being an astronaut?
Oh, yeah. You know, the early space flights were taking place. They were landing on the moon. This was heady stuff. And I thought, what an amazing adventure it would be to be involved in that, if only I could. But of course, for a kid from Adelaide, what are the chances? But it wasn't until later in life, after I'd developed some professional credentials and a career, that I realized I could actually apply. And I then went about methodically building up my professional resume so that I thought I could put a credible application in, which I did. And sometime later, succeeded in getting an interview to become an astronaut, from which I ultimately got selected.
Amazing. So tell me about this skill set that you built up. So what did you go about studying and training in before you sort of ended up in the astronaut program?
Well, I had a very good mechanical engineering degree from the University of Adelaide, and I'd worked in aerodynamics for a number of years, but I knew I needed something that was more space-oriented. So I changed professions, moved to California and got a position at the Jet Propulsion Laboratory, which is in California, working on science in support of the shuttle program, and I learned everything I could about space science and microgravity science, that we sometimes call it. And that, I think, was really instrumental in letting me have a credible application to become an astronaut.
So you get that grounding in sort of the science and the engineering, and then obviously being right there in JPL.
That's right.
So in total, you flew 4 missions to space?
Correct.
Fantastic. And how many days or hours did you clock up in space?
All total, it's been something like 170 days, but perhaps the most memorable of those flights was, in fact, my second flight. The first flight, it was memorable because it was the first flight, but the second flight was perhaps professionally the most significant one, because I preceded it with a year training in Russia to become a cosmonaut. And then I flew to the Russian Mir space station, which was flying at that time. It's since been deorbited. And I got to spend 20 weeks on the Mir space station with 2 cosmonauts. And that was just an amazing experience. It really was. Once I settled into the routine of it, it turned out to be a really good experience.
Wow. Can you tell me just a little bit about the moment of launch? Because I think for me, that's the most just impressive moment. You know, there's obviously months and months and years of planning, but at that moment where it's 0-1 and we have takeoff and you're strapped into this gigantic rocket with, I don't know how many, pounds of thrust.
You are strapped into 500 tons of high explosive, and someone's about to light the fuse. You lie there for some hours before the launch, waiting for the count to proceed. At about 10 minutes before the actual launch time, you get a call to close the visor on your suit and start your oxygen flow, and that's when you know things are getting serious, And then it gets quiet and you wait. And at about 6 seconds before launch, the main engines are started. And they run up to full speed for what is the longest and shortest 6 seconds of your life.
Imagine.
And you're sitting there and you can feel the thrust because the whole vehicle's swaying. It's still bolted very firmly to the ground. It's just swaying there under this tremendous force. And then at liftoff time, which we call T0, there's this huge explosion around the bottom of the vehicle as all the bolts holding you down are just explosively released. And the solid rocket boosters come to life, and you just roar upwards. You feel yourself slammed into the back of the seat. Everything starts shaking, huge vibration. Your teeth are chattering. If you're by the window, you see clouds just rush by the window, and the sky gets steadily darker and darker and blacker and blacker. At about 2 minutes into the flight, the solid rocket boosters are done. And so the whole vehicle's bathed in fire as they're explosively released. And then you just sit on the main engines and you just ride the main engines with this smooth ride, going faster and faster, pushing you harder and harder back into the seat. And you can hear the speed being called out in increases not of hundreds of miles an hour every few minutes, but thousands of miles an hour. And then at 8.5 minutes into the flight, the engine shut down. You've depleted all the fuel. The engine shut down. It gets quiet suddenly. And any loose objects in the cabin float up.
Suddenly start rising up.
And you're in orbit. And you're traveling at 28,000 kilometers an hour after just 8.5 minutes. It is the ride of your life.
Wow, that is amazing. I can see why everyone wants to be an astronaut. And on that, I suppose, for any kids watching, maybe young adults, what advice would you give them today, I suppose, if they wanted to get into a space program? I guess there are many around now. It's not just America, obviously, going to space.
Right.
What sorts of things should they do? Should they study? Where should they go?
Yeah, you need to get a good degree in the engineering or the sciences or medical sciences. You need to work in the aerospace industry and build up professional credentials. But the main thing is to get a good education, because that's, for me, that's what opened the door for me, and that's what will open the door for other people. And if you have a dream, pursue it. Don't give up. Figure out a path forward and follow through with it, because in that process, doors will be open to you that you can't even begin to imagine.
Well, it's probably a little bit late for me, and I'm probably a little bit too tall to fit inside one of the rockets, but it's been great living vicariously through you. Thanks so much for coming on,
My
Scope.
pleasure. Thank you.
How do you follow something like that? Well, we can try, right? How about unraveling the seemingly mysterious phenomenon of black holes? Or building your own constellation? You know what? That sounds pretty good. Stay tuned for all that and more. Hello there and welcome to Scope in Space. Yes, a whole episode about space. But which space? Is it this space? The space in there? Perhaps the space behind me? Well, none of them really. Of course, it's that space beyond the Earth's atmosphere where there is really nothing. I say basically nothing, but of course there are things out there. Things such as planets, moons, stars. The odd meteoroid, asteroid and comet do occasionally interrupt the vast void. But what about black holes? I mean, are they something or nothing, as the name kind of implies? Well, thankfully we have Dr. Tamara to translate the astrophysics for us.
Black holes appear a lot in science fiction, but how much of that translates to science fact?
Hi, I'm Tamara from the University of Queensland. I'm an astrophysicist, and today we're talking about one of the coolest phenomena in the universe, black holes.
One way a black hole is formed is when the centre of a massive star, one that's at least 20 times the mass of our Sun, collapses in upon itself. The star explodes in a celestial event known as a supernova, flinging most of its matter off into space, but leaving behind an incredibly dense core.
But this core can have a mass about 10 times the mass of our Sun, and yet it's squished into a sphere about the size of a small city. That incredible density means it has an enormous gravitational field, so strong that nothing can escape. Not a moon, not a planet, not even light. So if no light can escape from a black hole, how do we even spot them in pitch black space?
Well, say a star drifts too close to a black hole and it gets caught in its gravitational pull. As the star gets closer, it gets torn apart, and when that happens, the star heats up, emitting X-rays that radiate into space. These X-rays can be detected by our telescopes and scientific equipment here on Earth.
Black holes come in all shapes and sizes, but there are three main categories.
Primordial black holes are the smallest and are about the size of an atom. Despite being so small, they weigh about the same as a mountain. Stellar black holes are the second largest and the most common in the universe. They're often more than 10 times heavier than our Sun. Then there are the humongous black holes that lurk at the centre of galaxies. These are known as supermassive black holes and can weigh billions of times as much as our Sun.
Check this out. Our closest supermassive black hole lies at the centre of our very own galaxy. And this data is some of the best evidence that we have for it.
Here you can see a video astronomers made of the centre of our galaxy. As you can tell, the stars seem to be orbiting something that we can't see. Guess what? That's the black hole.
So I bet you're wondering what your chances are of getting sucked into a black hole. Well, the good news is it's pretty unlikely.
The only reason black holes are able to drag nearby stars toward them is because of their gravitational pull. In the same way that our own planet drags passing space rocks down to Earth in the form of meteors. So if you don't get too close, you should be fine.
In fact, if you replace our sun with a black hole that has the same mass, then apart from being a lot colder and darker, not a lot else would change. The planets in the solar system would just happily keep orbiting. But let's say, hypothetically, you did fall into a black hole. What would happen to you? Well, the answer kinda has something to do with spaghetti.
Astronomers call this spaghettification. The gravitational forces on your body would increase dramatically as you head towards the centre of the black hole. So if you're going in feet first, your feet would actually get pulled more strongly than your head, stretching the rest of your body out, just like a piece of spaghetti.
Spaghetti aside, we're learning more about these mysterious celestial objects every day. Just this year, we saw black holes directly for the first time. We didn't see them by light you can see with your eyes. We detected them by the ripples that they make in space itself. Sound strange? Well, it is.
They're called gravitational waves, and by using super accurate lasers, we were able to measure these ripples and then turn it into something we're able to hear. And it sounded a little something like this. That's the sound of two black holes colliding.
The more we learn about black holes, the more secrets they reveal about the rest of our universe.
We'll have more on the weird things that happen when black holes collide later on in the show. I certainly hope you can wait around that long. But right now, how about some science that you can get your hands on? DIY science, in fact.
If you look up at the sky on a clear night, you'll see billions of stars shining down. Some of these stars can form patterns called constellations, which can take the shape of an animal, an object, or even a person.
But if you don't know what you're looking for, these constellations can be pretty hard to find. So why don't we have a closer look at these shapes with the help of a special map?
To make a constellation geoboard, you'll need a template, a round cork trivet, glue, ball head pins, and a few rubber bands.
The first thing we need to do is cut around the outside of our constellation map.
I'm using the constellations in an area known as the Southern Hemisphere because if I look up at the night sky, these are the constellations I'll be able to see. People in different parts of the world will see different stars depending on which side of the equator they are.
This invisible line around the middle of the planet is called the equator, and it divides the Earth into the northern and southern hemispheres. So if you look here, you'll see Australia is located on the bottom half in the southern hemisphere.
Okay, so next up, smoothly cover the surface of the trivet with the glue. Then you can attach your template to the cork and dab the edges to make sure the template is really stuck down. Now all we need to do is to leave it to dry.
Then comes the fun part. We can place the pins on the star points and then add the rubber bands to form the outlines of the constellations.
I'm going to start with Orion because it's one of my favourites. It's named after a hunter from Greek mythology and can be seen throughout the world because it sits right on the equator. It can be seen in the northern hemisphere during winter and the southern hemisphere in summer. It's also really easy to find, which makes it handy for working out where the other constellations are.
Pretty good, don't you think?
There are a total of 32 constellations on this map, including the star signs Aries the Lamb and Taurus the Bull. A few of these constellations can be viewed all year long, but most are seasonal and can only be viewed at certain times of the year.
So, with a keen eye and a bit of practice, you'll soon be able to map out all these constellations and really impress your friends.
Remember, you can re-watch that DIY science on our website if you happen to have missed any of the important details. In fact, if you're quick, you might be able to squeeze in and now, but don't take too long because coming up on Scope, we're going to check out gravity waves and other current cosmic goings-on. Plus, we blast off with some reusable rockets. Well, see you soon. Hello and welcome back to Scope. I kind of feel like a space has developed between us. Do you feel it as well? Perhaps it's because this whole episode is all about space. Outer space, that is. And all sorts of galactic goings-on in science. And there is a lot going on out there at any one time. And much of it we can detect or observe from right here on Earth. Well, not right here so much, but, well, there's a place with lots of big dishes and antennas pointed up. I'll see you soon. Well, I've taken a quick trip down to Canberra, well, just outside Canberra, to the Deep Space Communication Complex to try and find out a little bit more about something that at least originated in deep space, gravitational waves. Glenn Nagel, can you tell me a little bit about what they are?
Gravitational waves are something that Einstein predicted 100 years ago. The idea that massive objects in space, like black holes or neutron stars, orbiting around each other, would actually cause ripples in space and time.
So Einstein predicted them that long ago, but it's only just recently that we've got experimental proof or evidence?
Yeah, the first concepts to actually detect these gravitational waves came out about 40 years ago. But it's only in the last decade that we've been able to build instruments fine enough, sensitive enough to actually detect these little tiny distortions in space that you and I would never ever notice. But these little instruments can measure variations as small as 1,000th the width of a proton at the core of an atom.
Wow, okay, that's crazy small. Now, I guess unlike, say, a wave in the ocean, a gravitational wave must be hard to detect because it literally ripples everything. The Earth, everything it passes through is moving at the same time, so the detector must move as well.
Yeah, well, imagine we've got a ruler in between us and we measure off the little marks.
Yep.
So what gravitational waves do is they stretch and they squeeze that ruler. But we wouldn't notice it because we would be stretching and squeezing at the same time as those measurements. So you need something that can actually measure something that cannot be seen.
Okay, this already sounds pretty tricky, but we managed to do it. The LIGO detector did it. Can you run us through, just very briefly, how it managed to do that?
So LIGO is actually two detectors, two 4-kilometre long tubes, sort of at 90 degrees to each other.
Sort of L-shaped, sort of
And
L-shaped
big
tubes.
L-shape,
Yep.
yeah. So what they do is they bounce lasers back and forth down those tubes off little tiny mirrors that are very accurate, and that CSIRO had a big role in actually helping
great.
make
Yep.
those mirrors. And what they watch for is not the distance that travels, but the time it takes for the lasers to travel back and forth. So if a gravity wave goes through, you'll get one distorting this way, getting shorter, so that it takes less time. The other one stretches, takes more time for that laser to go back and forth. With two of those detectors separated by an enormous distance, right across a country, say, you can watch for these waves and know it's not just something like somebody walking by that detector. You can look for the waves at both.
So the L shape is so that, yeah, you've got the different axes there and you've got then two detectors to see the gravitational wave pass from one to the other. So that, when you say they're 4 kilometres long, it must be 4 kilometres to some incredible precision as well.
Yeah, they have to actually have a variation that is literally smaller than the width of the core of an atom. You really have to have this high precision across this enormous distances to be able to bounce these lasers. And even just the mirrors that we made here in Australia with these fine coatings, again, thousandths and thousandths the width of an atom's accuracy.
No wonder it has taken so long to detect these things.
Yeah, it's just never been possible before. And of course, with two, we're able to determine the direction of which that wave came from. And that allows us to figure out that it was those black holes deep in space, billions of light years away.
A couple of black holes converging sent these ripples out, and then however many years later, they've rippled through Earth.
Yeah, to then reach us here on Earth. And if we can now detect those sorts of ripples, we can look even further out into space, further back in time, and maybe look for the ripples that were created in the Big Bang that started the whole thing.
Oh, I see where this is going. Well, thank you so much for your insight. It's been fascinating. Better duck back to the bunker. Right, well, that was a quick trip. I guess flying places these days, well, it's a pretty common thing to do. In fact, I looked it up, there's about 100,000 passenger flights around the world every day. Amazing. Although, can you imagine if at the end of each flight, they took the aeroplane, scrapped it and brought out a new one? Well, that'd be crazy. Although that's kind of how things work with rockets these days. Or maybe not for too much longer.
1, 0. And liftoff.
There's nothing more amazing than watching a huge rocket take off into outer space. But for every one of those big rocket launches, did you know there can be up to 20 small satellites that tag along with them? But we want to find a way to launch small satellites on their own. Hi, I'm Professor Michael Smart from the University of Queensland, and I'm going to talk to you about a project where 1, we can launch small satellites on their own, and 2, we can bring the rockets back to be reused. The current rockets cost millions of dollars to make. They are launched once and usually land in the ocean somewhere, never to be used again. This wastes lots of money and resources. So we wanted to design a rocket that could be launched and reused again, so we wouldn't have to remake one from scratch. But this requires a whole new design, something we call the ALV, or the Austral Launch Vehicle. The vehicle here today is the subscale test vehicle. The real one will be much bigger. It can be launched into space like a rocket, deploy a satellite, and then re-enter the Earth's atmosphere, landing smoothly like a plane. So here we have the ALV vehicle. The body of the ALV is just an empty rocket casing, so the rocket that's taken the satellite up into space. At the front, we have the propeller motor, which is going to bring us home. And at the back, we have some all-moving fins that help us to control the vehicle. And of course, on top, we have the swing wing. The swing wing is around 2 meters long and lays vertically along the rocket during launch. But when ready to come back down to Earth, this wing swings out just like a plane. When the ALV is in return mode, we can then take control, just like a UAV, using remote control to land it safely. Recently, we took the ALV out on a test flight, and we learned that we could fly and control it just like a plane. So what's so exciting about this project is it could be Australia's chance to get the foot in the door of the space industry. Did you know that Australia has not launched a satellite from Australia since the 1960s? So the small satellite market could be our opportunity to get back into this industry. So reusable rockets like the ALV could help us to save lots of money and resources. And they also could be our one giant leap into the space industry.
Well, I hope you've glided safely back down to Earth. But before I switch off the seatbelt sign, I'd like you to take a look at our in-flight video with some highlights of today's show. We heard from Andy Thomas about his life as an astronaut, saw some of the mysteries of black holes unravelled, and we found out how we finally tracked down gravitational waves. If you missed anything from today's show, well, the signal is probably well and truly out in space by now, but the content lives on our website, so check it out. And don't forget to get all interplanetary next time when the ordinary becomes extraordinary. Under the scope.